Hello everyone, my name is Björn Dase. I'm a master student at the Hasso-Plattner Institute in Germany, and today I would like to present our paper Maximizing Persistent Memory Bandwidth Utilization for OLAP Workloads to you. It was written together with Lars Jonas Bollmeier, Lawrence Benson and Tilman Rabel of the Data Engineering Systems Group. Overall, our paper is about the evaluation and optimization of PMIM for OLAP workloads. Due to time constraints, we'll just have a look at some spotlights of it today. Therefore, we'll first have a look at PMIM, then what happens if we drop and replace DRAM with PMIM in a typical OLAP workload, and from these results start a detailed evaluation of PMIM bandwidth, with finally providing a set of best practices as optimizations for PMIM bandwidth utilization. Before coming to PMIM, we'll first have a look at traditional storage technologies, DRAM and SSD. First, let's have a look at DRAM. The advantages of DRAM are its byte addressability and the high bandwidth it provides. However, the major disadvantage of DRAM is its low memory density. On the other hand, we have SSDs. Its advantages are that it's persistent and provides a high memory density. The disadvantage, on the other hand, is the low bandwidth. There we see a PMIM DIMM, nearly looking like a normal DRAM DIMM, which combines the best of both worlds, the DRAM and the SSD world. It gives us a high memory density, provides us with a high bandwidth, comes with byte addressability, and the data stored on it is also persistent. On the left, you see an implementation of the SSB in Hi-Rise, a state-of-the-art OLAP database management system. In one run, it uses DRAM. In a second run, PMIM is used as a drop-in replacement for DRAM. We see that as a drop-in replacement, PMIM performs significantly worse than DRAM. But if you implement a handcrafted SSB with many optimizations, which you can see on the right, the performance of PMIM is significantly better and already close to that of DRAM. Therefore, optimizing access to PMIM is an important topic in which a lot of bandwidth can be gained. When you now depict the sequential write bandwidth of PMIM in dependence of access size and thread count on the X and Y axis, you would normally expect an increase in bandwidth with a growing access size and thread counts. But as we can see from this graph, PMIM behaves very unexpectedly and with non-typical patterns, e.g. already peaking at 4 and 6 threads. In order to optimize the bandwidth utilization, therefore, one first must understand the PMIM behavior in detail. Therefore, it is essential that we carry out an extensive set of micro benchmarks in order to understand the behavior of PMIM in detail. First of all, we'll have a look at PMIM during sequential reads, then during sequential writes, and last but not least, we'll examine how PMIM is affected by non-uniform memory access, the so-called NUMA effects. Due to time constraints, not in today's presentation, but also in the paper, are read and write thread pinning benchmarks, benchmarks investigating the performance of mixed read and write workloads, and last but not least, benchmarks looking at random reads and writes. As a first step, it is important to look at the structure of a typical OLAP system. Our system consists of 2 sockets, each occupied by an Intel CPU. Each of the CPU has 18 physical and 36 logical cores. This totals in 72 cores for the full system. On each socket, 6 PMIM DIMMs are connected, giving us 12 DIMMs in total. Each DIMM has a so-called write combining buffer on it, allowing to buffer and batch successive writes to improve performance. The DIMMs on one socket are interleaved in 4 kilobyte chunks with each other. Always 3 DIMMs are connected via one IMC, sharing this IMC with 3 DRAM DIMMs, which means the system also has 12 DRAM DIMMs in total. The system is running Ubuntu 18.4. So let's start with the sequential read access now. When examining sequential memory access, one must first differentiate between two basic access patterns: grouped and individual access. Grouped access works as follows. Given a memory region, in this example having a size of 8, and 4 parallel threads accessing it, in the first read cycle, threads 1 to 4 read the first 4 memory regions, determined by the access size, lying one behind another. In the next read cycle, they will all at once and read the second 4 memory regions, lying one behind another. Examining this read behavior in dependence of the thread count and the used access size results in the following bandwidth. The access size in byte is on the x-axis, the bandwidth in gigabytes per second on the y-axis. The different lines represent the different thread counts. As we can see, more threads generally improve the bandwidth. However, utilizing all physical cores is enough to fully saturate the PMEM. Regarding the access size, the behavior is more nuanced. Using an access size of 4K gives the best overall bandwidth. Using a smaller access size severely reduces the bandwidth, as this makes the individual threads all accessing the same PMEM DIMMs, and therefore not utilizing the interleaving of the individual PMEM DIMMs. The clear drop in bandwidth with 1K and 2K access sizes is also noticeable. This is a problem of the prefetcher, specifically the level 2 hardware prefetcher, which is absolutely catastrophic for these cases. If you deactivate it, you can see a straight rise to the 4K. Now let's have a look at the second access pattern, individual access. Here, each thread reads a continuous memory region. The first thread reads the first quarter of the total memory, the second quarter, and so on up to the fourth thread reading the last quarter. Again, we see the graph with the same parameters and the same labeling. Here too, we see the same effect with regarding to the number of threads. However, the bandwidth curve is much more even regarding the access size, which makes sense. Due to the individual access patterns, the PMEM DIMMs are accessed in an interleaved manner and thus making the access size irrelevant. Furthermore, the prefetcher does not have any problems in this configuration, which is also beneficial. In summary, we can say what is already written in the title of the slide. After an initial increase in bandwidth for all thread counts with an increasing access size where we see a lot of write amplification, the bandwidth then remains approximately the same or only decreases slightly. In particular, we can see that already 4 to 6 threads are completely sufficient to fully utilize the PMEM when writing. This is due in particular to the good use of the write combining buffer in this case. Since we only have a few different threads and therefore only a few different write points on the PMEM where things are written, the successive writes requests can be combined well. Now, on the right, we'll have a look at the larger thread counts. Again, you see the smaller thread counts being grayed out. In contrast, we see here that with a large number of parallel threads, smaller exercises are to be preferred. Nevertheless, the maximum write bandwidth is still lower than in the left case. The reason for this is twofold. The first reason is that the write combining buffer cannot work well for big requests at too many different write points and therefore cannot utilize it very well. The second reason is IMC contention. As write operations are masked by the IMC, the application can issue a significantly higher number of requests than the underlying storage medium supports and therefore produce contention. Finally, we can say that one should use 4 to 6 threads for writing to PMEM to reach the maximum bandwidth. Last but not least, we'll have a look at the NUMA effects when reading PMEM. On the left, you again find our system overview. On the right, you find the performance of the 5 possible different configurations when having 2 sockets, and then reading across memory sockets. Again, the y-axis represents the bandwidth. On the x-axis, we see the different thread counts. The use exercise is 4K. Let's start with the orange line, representing the near axis. It looks as follows. It reflects what we have already seen in the analysis of the sequential reading. The bandwidth increases relatively steeply up to the physical number of cores, after which it remains fairly flat or decreases just slightly. The next configuration we're going to have a look at is the 4-axis, represented as a green line. The bandwidth is consistently minimally lower than with near axis, which can be explained by the increased latency with 4-axis. Next, we're having a look at the blue line, threads on both sockets accessing their near PMEM respectively now. In this configuration, we see a nearly linear scale-up in bandwidth in comparison to the one near line. However, the situation is different with bilateral access to far PRAM, the black line. Here the UPI represents the bottleneck. If you analyze this configuration with Intel's vTune, you can see that it's almost 100% full. Metadata transfer represents around 25% of the UPI load, leaving only around 60 GB per second for non-metadata transfer. Redoing the same experiment with DRAM instead of PMEM shows the same cutoff at 60 GB per second, substantiating the result. The last configuration in gray is trying to support near PMEM worker threads with fast threads reading from the same PMEM. The bandwidth in this case is catastrophic, which is due to the constant reconfiguration in the cache coherency protocol in this case, which is used between the 2 CPUs. In total, this boiled then down to the statement that threads should only read data on their near socket. If this is not possible, it should at least be stable instead of changing across sockets. So let's have a look at how these learnings then look as actionable best practices. First, one should read and write to PMEM in distinct memory regions. Second, the number of threads should be scaled up to all the physical cores when reading, but limited to 4 to 6 per socket when writing. Third, data should be placed on all sockets, but only accessed from near PMEM. Additionally, not in the presentation, but also in the paper, are guidelines for pinning, read and write mixed workloads, random access, and the usage of DevDux at the PMEM operation mode. If you're interested in the details, I invite you to look it up in the paper. In total, we have seen that our research boils down to the following facts. First, For reading the shown benchmarks in addition with many additional benchmarks, including replications on DRAM, show that PMEM behaves pretty much like DRAM and therefore can be treated very similarly. However, especially when writing to PMEM, it shows very unexpected behavior that differs significantly from DRAM. It is very important to understand this in detail to get the maximum bandwidth utilization. Third, when following the 7 best practices we have presented on the last slide, we have seen that we can highly increase the bandwidth utilization on a multi-CPU NUMA OLAP system. As said in the beginning, we wanted to bring PMEM into an order of magnitude with DRAM. To measure this, we implemented the star schema benchmark and applied all our learnings. As a result, we get PMEM being only 1.66 times slower than DRAM when implementing the SSB. That's it from our side. If you have any questions, please feel free to ask them now or write them in the chat. For all the detailed benchmarks, many comparisons to DRAM, and more in-detail explanations and discussions, I invite you to read the paper. And I also invite you to check out what's behind the QR code. If there occur any questions in the future, please feel free to drop us an email.